Dear friends, hearty welcome to the online problem solving session series organized by Maths Aspirants. As you may know, Maths Aspirants is a collective of math lovers initiated by myself in 2017, and we used to organize several programs to promote and popularize mathematics among students. As a part of the online problem solving session series, today we have a session on ring theory, and we're blessed to have Dr. 𝐷𝐢𝐭𝐡 with us to handle the session. Dr. Jayakumar recently awarded PhD from Institute of Math Science, Chennai, and his broad research area is abstract algebra. Jayakumar already taken some sessions in our platform. All that sessions are available in our YouTube channel. So in today's session, he will discuss some part of ring theory and some problems from the previous year question papers of 𝐷𝐢𝐭𝐡 exam. I'm sure that this session will be really helpful for those who are seriously preparing for these kind of exams. I would like to express my sincere gratitude to Dr. J for accepting our invitation and joining with us. I welcome everyone to this program. Welcome, J.
Thank you so much, Vinod sir. And I many times I gave a talk here, okay, and still I love to give a lot of talks because the important reason I came through this kind of classes in Chennai when I completed my BSc. I have no idea what direction I should take. People are pushing me towards this MBA and other things, okay. Then suddenly something happened. Then I went to IMSc and attended a simple free class, and they were my seniors were kind enough to guide me exactly like this class. Whatever happening here in virtually, that happened in a person offline kind of thing. Then I got seriously motivated, okay, and that is the main reason I like this group and still a part of this group, and I wanted to contribute more things, okay. So another thing, as I said before, the learning is not going to be complete unless we start teaching. At least we have to be ready. So here actually I will not say it's teaching. I rather say it is like sharing the experience. Some of them I prepared here are from the basic. It is going from the basic step by step. Some things you can just see and answer them. So there are 10 questions I prepared like a supportive. 5 questions I prepared directly from the exam, true or false questions, right? So all of them we will try to solve one by one. At any time, if you have a question, you must stop me and ask me, okay. So initially what we will do, we will recap something, and after the recap, each and every question, this 5 questions from TFR, not at all easy. For example, there is one question about RXY. That situation may not happen, in fact almost never happen, still they are asking question. There are some reason in that, okay. So I added some kind of a fun fact, each and everything. So I'm trying to use the language that is more relevant to you people, very young people, right? But those are not just fun fact, those are much more in it, okay. In the notes, whatever I have written, as I said, it is not a traditional way of doing, but rather it complete the traditionality, okay. So this is what I want to do. So now I'm going to share. Okay, so as I said, I wanted to start from recapping the idea of ring theory. In the notes also I included, this is not it, this is actually complement, not like a substitute of something for traditional way of teaching, okay. We need it. And I also at the end I wanted to share about something plus about AI. Right now what is going on, I used AI, okay, for this. This is a presentation. The notes is already there given to sir. He already shared, and I will also tell something about negative of AI. Okay, what happens when the one if somebody rely on AI too much, it is also problem. Okay, how one can use AI for this, okay. So you have to observe that thing also. The way I prepared, I have everything in my mind, but AI helped me to materialize, okay, plan and everything materialize, okay. So let's start with the ring theory first. So I'm assuming you must done little bit of ring theory, like knowing what is ring, what is everything. Okay. In the higher level also, we will read again group theory, ring theory, and everything. Even in my PhD, not only in my undergraduate, in my masters also I read. Even in the PhD. Okay. But in PhD, our point of view are different. Okay. First prototype. Okay. The first question when I faced in abstract algebra course, what is definition? What do you think about the definition? They want me, my professor want me to take the perspective of the definition, which I have no idea as a master student. Then three, four students were started discussing, and we come to know that actually definition means we have some prototype examples. For example, in ring theory, Z is the prototype. Often in group, in a cyclic group, they try to relate with Z. They try to relate with the Z. May not be, uh, isomorphic, but why they are doing it? Because Z much more visible. The same thing happening in the ring theory. We take Z. Once we have a Z, and we can abstract the definition, and we will get the ring. Once we have the abstract the definition, people try to search for it. And the moment we lose the commutativity, this M1 of R or maybe M1 of C, these are becomes main prototypical examples, and later on M1 of Z2 or Z10, all those things. Okay. So I believe that ring. So basically, I don't want to teach you everything from the core. Basically, ring is a non-empty set where two operations are there, and each operation behaves very nicely. Okay. So we going for prototypical example only. These are called mental angers. So in the olden days, people use prototypical example, but nowadays people use this word mental angers. Mental angers means we have to have the anger, right? Like a ship making the anchor, and it won't move not too much from the anger, right? Similarly, ring theory won't move without this example. Whatever you come up with the idea, try to apply on these things and see works on. Then we have a special rings. These are called Gaussian rings, and you will see this has some very beautiful properties and so on. Okay, so we have an example. So what are the example for infinite level Z, Zi, and Q? Q is a field, a nicer ring, very very nice ring, and we have this kind of things that finite rings. Okay, these are the prototypical example. And of course, when something is indexed by natural number, it is more appropriate to ask what happens when n equal to prime. You will see this kind of examples are really important once you go to in the field theory. Okay. Right now we are in the ring theory. We are focusing only on the rings. Okay. Once in the level, the ring introduced, example introduced, some of the property introduced, right? Once all this property introduced, what we summarize the next one is special types of ring. And most of our example lying on this, all this commutative algebra example, all things lies on this. Okay. So we have an integral domain. What is integral domain? No zero divisor. Let's understand what is not a zero divisor. For example, in Z6, we have modulo addition 6. What is the thing here? I have to, for example, 2 equal to 4. That's okay. 2 into 2 into 2, actually 8, but I have to restrict that into modulo 6. That means I will put the remainder only 2. Basically, it's like that. But look at this. 2 is not a zero element. It's not a zero. And 3 is not a zero. But when I multiply, I have a 6, which is congruent to 0. Remainder 0 mod 6. And two non-zero elements, when I multiply them, giving zero element, right? So that is called a zero divisor, something like a divisor. So I can split this into two non-zero thing, and that as actually combined into zero thing, which I don't like it. For certain reasons, certain really, really deep reasons, we don't like it. So when I have a ring without a zero divisor, that means whenever I have a AB equal to 0, either A equal to 0 or B equal to 0. If this is the sense, we say it's an integral domain. And when we have an integral domain, and every non-zero element has a multiplicative inverse. I'm only talking about non-zero elements, like a Q. Z is there. Z is not a, actually Z is an integral domain, but not a field. For example, 2 has no inverse. The 2 inverse is 1 by 2, which is inside the Q, not in Z. So one of the distinctive example is Z to Q. Q is actually filled. Every element has an inverse. And this is the way to define the notation of index. If R is a ring, then we will say that R power X in the multiplicative symbol. We say it is actually units. So basically, what I'm trying now, giving you the terminologies, taxonomy, and the correct what like notations, so that it's easy to understand the question. Most of the time, what we do, we don't even understand the question. We struggle to understand the question because of no correct language. So what I did actually to create these notes, I took 5 questions from TFR exam and I put them as a center and constructed these notes. Okay. So fields basically integral domains. If you know the fields full definition, you can see that it is easily integral domain, satisfying integral domain thing. And this is one of the thing. Rx is actually a group. What is Rx? Rx is set of all A belongs to the ring such that A inverse also exists. I'm just collecting those are invertible. Of course, I'm assuming one is there in my ring. Then it is non-empty. Then only it is making sense. Otherwise, defining the inverse is not a thing, right? It is implicitly assumed. And one of the things what we do actually, whenever I have a very big object, I try to break my object. In group theory, what we do, we say something. Have you ever wondered why certain groups are called normal subgroups? The word normal is actually something very rhetorically looked into in group theory, right? Why? Just think about this question: why certain groups are called normal groups, and why people are obsessed with the normal group? Try to search in the internet; you will get a lot of answer, and you can summarize them. Really, those are the normal groups. Similarly, in the ring theoretical way, not all the subrings are we are interested. We are interested in certain subrings, and in that certain subrings, suppose that identity should not be there. That is one of the very important thing. Okay, sometimes definition of subrings of some books include the thing. That's why we don't want to even say what is subring, but we want to say what is ideal. The word ideal also very equivalent to the normal subgroup. Something ideal. In an English way, something ideal that can operate. Basically, what happens? Ideal, its own subring within looked into. Okay, you look into that, it's actually own subring. It may not be subring in the sense of R, but it's in the subring in the sense of its own. Okay, you have to go little deeper what I'm saying to understand this. Okay, then this becomes actually a ring. I have a ring, I have a ring, and in some way, this R is somewhat of making a communal way, and we will like to understand what happens in this way, right? If this is a ring, I is an ideal, and R by a ring, and if it is a domain means integral domain, ID or field, and that's something nicer about, we can say nicer about I. In fact, that is our definition in the commutative ring with identity. Suppose I have a ring which is commutative. This is not a traditional way, okay? In the commutative ring, an ideal, again, it is not a way of nicely written, but in for our purpose, it's to R by I is integral domain if and only if I is prime ideal. If you don't know what is prime ideal, forget about it. Take this as a definition. Then R by I is field, that is also ring field if and only if I is maximal. There are beautiful definition about prime ideal, maximal ideal is available, but right now you take this as a definition because we are working in the setup of commutative setup. All these questions are taken from the commutative setup only. Okay, so here the actually the definition I wrote in from the notes. Notes contains all the definitions. All of them are clear. Okay, very depth. You can go with that. Okay. The word observe is very important. Let's spend 1 or 2 minutes about that. The word ideal is very equivalent to say something normal. I want something, some candidate like an ideal. The ideal means when I say it is actually closed under addition. Not only that, it observes the multiplication. Means if you take something from R, something from A, this RA belongs to I. And as I said, I'm only interested in commutative rings. It's equal to AR. So no need to say like that. Okay. And the prime ideal definition is like this kind of prime number definition. What is a prime number? If A divides P and P is a prime number, then A must be equal to 1 or A equal to P. And if you little bit twist this matter in terms of ideals in Z, you can see this is the definition. If AB belongs to, in another way, I can say like that. If P divides AB, then P divides A or P divides B, which is not true for not prime numbers. For example, 6 divides 6, which is 2 into 3. But 6 does not divide 2, 6 does not divide 3. But prime number has a special property. Whenever P divides AB, then P divides A and or P divides B. Any one of them, sometimes both. We don't know, but sometimes both. Okay. And the maximal ideal definition is that strictly between nothing strictly between I and R. Suppose I is an ideal in R, which is observing multiplication. And if you see there is something in between, either that is equal to this or this is equal to the whole thing. And you can see that it is also resembling nicer way of prime ideals. That's why from this perspective, it is very clear. All the maximal ideals are prime because field implies ID, integral domain. Okay, so all the maximal ideals actually prime ideal. The converse is not true. One of the serious problem about uh, converse, often people try to mistake the definitions. Sometimes definitions start with yeah, ideal, which is not a trivial ideal like that. Some books have some definitions. But see, for example, Z in Z, 0 is actually a prime ideal. Why? Because Z by 0 is again equivalent to Z, and that is an ID, integral domain. That's why Z is actually, I mean, 0 is actually prime ideal by our definition. But the same thing is saying that because this is not a field, the same thing saying that it cannot be a maximal ideal. So keep this in mind in a mental anchoring way. This is one of the limitations. 0 is a prime ideal example, but not a maximal ideal example. Okay. These are going to helpful. These are going to be really helpful in our later question. Okay, so our ring theory actually starts with a general theory, then that contains special things about ID, integral domains, and there is something called PID in between UFD, ED. I will talk about this little bit later. Then it contains something called polynomial rings. So all this thing, okay, there was a very nice question. It's not like a question, it's a discussion type of question. One of our senior asked three of our people. I was one of them. He asked, what is the difference between classical algebra and modern algebra? Or nowadays it's called the abstract algebra, right? So we were discussing, telling some answers. Suddenly somebody said this thing. In classical algebra, we study most of them about polynomials only. Basically, it is motivated to search the roots of polynomial. You go and study from your school books, okay, classical algebra, wherever you can find something in it. In it, in the sense, some underlying philosophy is going on. It's all about polynomial. Whatever we do, it's all about a polynomial. But in modern algebra, really all about symmetricity. the basic motivation for group theory is actually symmetricity. Symmetric. People try to collect symmetric. You have a nicer object, collect the symmetric, that becomes a group. Basically, so it is motivated from the perspective of symmetricity, and that is perfectly aligned with the classical thing. Basically, the modern, whatever now we call abstract algebra, extend the classical view. So that we should really understand polynomials. In polynomial also, some of the things plays no interplay. Interplay means a polynomial looks like this: a n x power n plus a n minus 1 x power n minus 1 plus dot 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 n. So what is the most basic idea? Trying to search the roots of the polynomial. If I'm not able to find the roots of this polynomial, then the next question, I want to keep my base place. For example, x square plus 1 in real, or even q, just go for q, has no solution or root in q. It can be proved very easily. For real number, we need to do some little bit of understanding of analysis, positivity and other things, but here we can prove very easily. How can I prove very easily? You can see that if p by q, where p belongs to z, q belongs to natural number, and p comma q GCD is 1, and you project it, you can see that the q must divide this one. The p must divide the this one, sorry, the p must divide this one, the q must divide this one. This is called a rational root test. If you don't even know rational root test, yeah, that's okay. You can directly put p square by q square plus 1 equal to 0. That says that p square plus q square equal to p square. Sorry, I mean 0. And you do little bit of things, you can understand from something square positive, little bit of analysis. That way is also okay. It's not solvable. You can see that it's not solvable. Okay. So then people started asking the question, can I fix the q? Can I go little larger than q? So how larger I should go? Okay, before even real numbers. Remember, this is one of the very important fact. Before even real numbers, Gauss started working on this number, qi, which is inside zi, which contains zi. Sorry, I said something wrong. Which contains zi. Without even realizing about a lot of things about real, people started understanding this one, qi. And in fact, this is countable, which contains solution for x square plus 1, purely algebraically. So from natural number to whole numbers, by asking the completion, what is the nothingness? From whole number to z, by asking what is the negativity. From here to here, asking the multiplication thing. Then from here to here, analysis plays role. Again, from here to here, algebra. All of them are algebraic question. Only from this fact is analysis. And you can see from here to here, the countability, uncountability things start. Before that, there is no issue of uncountability, just everything countability. Okay, fine. Now, in the basically polynomial ring, we want to say something irreducible. Why do I want to go to the irreducible? In fact, in there we know no every number greater than or equal to n can be written as products of primes and powers, its powers in a unique way. If you fix the smaller number come first, the next prime, smaller prime come next, and it's a unique way, or up to the permutations of the places. Okay. Similarly, when we are working with the polynomial, our basic idea searching for the roots, right? Searching for the roots means I wanted to break my polynomial into several pieces as much as I can. And among the several pieces, I look into the pieces and try to get the roots. If f is g and h, if g has a root, then f has a root. And if the way of splitting is very nice, like a prime way, then we say If f has a root, then G or either H must have the root. In the way we wanted to split it. In other sense, we wanted to go as down as possible. That's why the irreducibility is coming. Okay. So what is an irreducible polynomial? Let me tell you what is an irreducible polynomial. If you return like fx equal to gx and hx with the degree of g, comma degree of h strictly less than degree of f, and degree of x is actually greater than or equal to 2, we can say 2, then it's reducible. That is, if we have a bigger degree polynomial, you can split the bigger degree polynomial into smaller degree polynomial, not 0 degree. 0 degree polynomials actually considered as a constant. Okay. Then it is a reducible polynomial. And if not, we call it irreducible polynomial. For example, x square plus 1 inside qx. It is an irreducible polynomial. It has no solution. In fact, also you cannot split them. In fact, x cube plus 1 inside q is not actually, so let me put 2 for that. It's not actually a, yeah, it is, I think I want to put like, no. Yeah, it is actually, I think it's irreducible. Yes, it is. So we have a lot of irreducible things. And I wanted to connect irreducible polynomial. I'm purposefully skipping this part because I want to say something. Suppose my polynomial f of x, listen carefully, this is one of the very important thing. So it's in a ring X, it's irreducible. All you need to know for this class, if and only if the ideal generated by f of x is an maximal, is a maximal ideal. That is if and only if we know, no? If it is a maximal ideal, this becomes a field. And I'm really interested in F only. So the basic question, I will start from a field and look into the f of x. And if it is having every solution here, it's okay. If not, I'm going to the irreducible part where it's not solution. Example, fix in your mind this one, 2 of x. Then this f of x is maximal. And that's going to give you a bigger field. And in this field, f is inside. This is the theory. I'm not able to prove because of the timing, but this is the theory. This is how we make a larger field. This is how Gauss came up with this idea. Now, when you extend something, we like to preserve a lot of properties. Okay. So the basic idea, I wanted to take the solution, but I don't want to set up the disturb. I don't want to I don't want to disturb the setup which is already there, correct? So Q is a field. I want something larger. Minimum thus must be a field. And it should have some nicer properties. So that's why again in ring theory, we started understanding what are other things. I have a field and integral domain. Between this integral domain and field, only one very important difference is every non-zero element has an inverse, then it's a field, right? Otherwise, it is an integral domain. I mean, every other things are satisfied with the integral domain. That's one of the very important things. When people started understanding anything you wanted to do infinite level, try to understand in the finite level. In the finite level, actually equivalent to field. There is no difference between integral domain and a field. Both are same as long as it's finite. The proof is using Bijumon principle. It's a nicer proof. Please read this in the standard books. But in the infinite level, it is not like that. And people are also wanted to understand if I have a field, is it a field? First of all, the question. Answer no, because X is not invertible. The indeterminate, often we call that indeterminate, it is not invertible. So how far we are? What are the things that is possessing from the field? Inheritage field weight. And they formulated those things, and it was aligned with the ring theory. So that's what we called ED. So we have ID here, integral domain, and a field. In between them, something called ED, something called PID, something called UFD. So ED means Euclidean domain, where you can do the divisions. We are going to talk a little bit about later, but let's understand the formal definitions. I will continue to those things. So what is PID and UFD? So first of all, ED, actually there is a norm, something called Euclidean norm is defined. With respect to that norm, we can divide. In Z is one of the best example of ED. So give me a moment. Let me erase this. So what is the function defined on Z? It is absolute value. Okay, so if A and B not equal to 0, I can divide A by B like this. BQ plus R, where this R, absolute value of R less than absolute value of B. In that Fx, this is also ED with respect to degree. Forget about 0, just leave the 0. Okay, we are not going to divide by the 0. Other than 0, all the constants are degree 0. All the constant element which is inside this F are called degree 0. And A power n, x power n plus dot 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 plus a n minus a1x plus a naught. This degree is assigned to be n. If a naught is a n is not equal to 0. Otherwise, it's 0, like in the constant level. Okay. With respect to this becomes an Euclidean domain. So basically, Euclidean domain, you can divide anything by non-zero element and get that norm less than the remainder. The norm of the remainder is less than the norm of the dividend. What you are the dividend. Okay. So you just keep this in mind. We are going to work on this. Okay. Okay. And another one of the thing about PID, it's called principal ideal domain. P for principal, I for ideal, D for domain. What is principal ideal domain? Every ideal singly generated. It is singly generated. Okay, every ideal is actually singly generated. Okay, that means there is an element inside that ideal which generates everything. That much is enough for you right now. Okay. Okay, then UFD is something called unique factorization domain. I will talk about this only if it is needed. Let's not talk about this right now. So far, okay, everything is okay. Should I explain something more? Can I continue?
Yes, sir.
Okay, so it's merely a recall. I'm really interested learning about this one. Okay, so this Zi are called Gaussian integers. Remember, before even knowing complex numbers, imaginary numbers, people from Q itself using only algebra started understanding Qi. What is this Qi basically? It is isomorphic to Q of x quotient by x square plus 1. There is no analysis that needed. No analysis that needed. Remember to do this. And it is fairly countable. It's nice and easy to countable. Okay, count. And inside this, we have Z. Similarly, Gauss and other people asking, what about this? And this is one of the example. and the norm A plus IB. A typical element looks like A square plus B square, A plus IB. So in often in algebra, we should ask this question: how do they look like? How can one can represent an element? If you want to solve questions from algebra, the basic underlying philosophy is how do they look like? What exactly I need to represent it? Then more or less it will do. And one of the beauty of this norm, as I said, I can take an element alpha, which is A plus IB, and beta, something like C plus ID, and let us assume that beta not equal to 0. Then alpha can be written as some Q beta plus R, where this norm of R less than norm of beta. Remember, this is very important. Using that, one can precisely prove, this is going to come, we are going to deal, precisely prove it has only 4 non-one element, okay, which are units. Units means invertible element. In case of Z, you can see, suppose A belongs to Z, A inverse exists. Then one can show that A must be plus or minus 1. If it is invertible, it must be plus or minus 1. In case of in Gaussian integers, if it is invertible, it must be plus or minus 1 and plus or minus I. No, none of the other elements going to help you, like going to be as an unit. Okay. So one question from TFR asking, do I have an ideal where Z by is infinite? Do I have an ideal where if I divide that ideal, I mean quotient that ideal with Zi, which is going to be infinite element? Actually, that is not true. We are going to see, and it has a connection with what I am telling here. Units are precisely this one. We will deal this question. And as usual, you know, right? Whenever we read something about structures and other things, we always wanted to show morphisms. So what is a ring homomorphism? Preserves addition and multiplication. I have a ring here, I have a ring here, and there is a morphism which preserves addition. A plus B equal to phi of A plus P of B. Just for naming sake, I'm writing A B equal to phi of A plus phi of B. And some people, and including me, assume that the multiplicative identity goes to, I mean, 1 goes to 1. We don't like to work in any ring other than unital. Okay, we always work in unital ring. 1 of R goes to 1 of C. 1 of, sorry, yes. And automatically kernel becomes an ideal. That is one of the time. The imagine is an inherent ring from the subring for the S. And we have a first isomer, just like group theory. That's why I'm not doing this. One of the important thing, this is the important thing, okay? The units of R, that is what Rx, the image, which is contained in unit of X. This is one of the simple yet powerful example. It is a simple example, simple observation, sorry. It's a simple observation, but very, very, very important thing. And it is not always true, even when the subject is that. Try to find the example. This is the first step. Try to find example. Okay, try to find example. Even that means you need to find a ring from here to here, another ring, give surjective ring homomorphism such that Rx properly sitting inside Sx. Try to find an example, okay? You see, very simple thing, no? But I'm sure ready-madely, without finding, can you come up with an example in your mind? Think about it. Think for 1 minute. Do we have this question? Like, do we have this? I have a subjective homomorphism. Still, can you give me an example of this? Subjective ring homomorphism. I have a subjective ring homomorphism. So if not, I will tell you. It's a very simple question, right? This kind of questions are very common in TFR exams, even in the interviews. So the answer I will. So shall I give the answer? Somebody has to say yes. Shall I give the answer?
Yes, sir.
Okay. Sometimes we need to think very simply. Take Z. Just now I told you how many things are there, no? Plus or minus 1. From Z to, for example, Z7. Can you think of a ring isomorphism? The obvious ring isomorphism is this one, no? I mean, subjective ring homomorphism. What I'm trying to say. Try to prove this is a ring homomorphism. And you can see every non-zero element is invertible here. Fairly you can see. In fact, 3Z. Take 3Z. You can just by hand you can prove every non-zero element. Basically in Z3, 0, 1, 2. We have only 2 elements need to check. You can check that both of them are. But if I go for Z5, then you can see that 2, 3, 4. All of them are invertible except 0. And you can see that Rx image is actually. So the 1 goes to 1 and minus 1 goes to where? You can think and you see that the cardinality is just 2 elements. Right? So, but the cardinality of, even though it's a surjective, the cardinality of, let's say, yes, Sx is 1, 2, 3, 4. It's 4. So even though it is a surjective, sometimes our definitions will trick us. If it is surjective, things are great, but it's not true. In the sense, that's why I put it this one. This is a very surprising one. I'm sure many of you not heard of these things. Okay. Okay, let's solve question one by one. So far we done theory. I wanted to pass a moment and ask you the question that if you have any problem, let me know. We can explain that, then jump into problems. Do you have any questions related to theory, whatever I did? You can also tell me that if you don't understand something, let me know. I can help you. Shall I continue then?
Yes.
Okay. So, okay, the problems are basic drill. First one, showing this forms group under the multiplication. And from the group theory, the reversal law. Just try to do this, okay? We wanted to show that Rx is a group. To show something is a group, and I'm assuming one is there. It's non-empty, first of all. Then we need to work on. If AB is there, what happens? Remember, this is not like a subgroup kind of thing I'm asking. I'm asking group. That's why we need to check all these things. Okay. The associativity coming from the definition of multiplication, which is from the ring. And one is there. By assumption, we assume the one is there. And everything invertible. That is what I collected. All you need to see the closure. If AB inside R, then AB also inside R. How it is? Look this. AB, B inverse, A inverse. Which is the identity. Because B inverse, associativity will tell you this. So this is AB inverse. So what is AB inverse? Whole inverse. I think that B inverse A inverse. By just writing one cancel. This is a very basic question, but still. Okay. Okay, for this question, I wanted to introduce something. Determine Z12 basically. What are the units of Z12? Okay, so let me ask a different question from school level. If I give you, let's say, 4x4 matrix, and I'm asking whether this matrix is invertible. If it is, find the inverse. What do you do? Even for 3x3 matrix, what is the first step? I will give you 3x3 matrix, and I'm asking you find the inverse. What did you do first? Anybody? 3x3 matrix given, and I'm asking you to find the inverse. What did you do? The step one.
First, check the determinant.
Right, very good. Why do you want to check the determinant?
If it is 0, then it is not invertible.
Yes. So I don't want it to, work on something determinant 0. If it is determinant 0, theory is telling us clearly there is no possibility of finding the inverse. So I don't want to work on really. If the determinant is not equal to 0, then I want to work on. And in linear algebra, you can understand little more than that. If I have a matrix over a ring, commutative ring, one is inside or commutative. Okay, commutative ring. You can see that the determinant function will tell you something beautiful. Det of A actually element of R, and A is inverse exist if and only if det of A inverse exists in R. For example, look at M1 of Z. Of course, you can get matrix. Okay, you can get the matrix. For example, do you think this matrix is invertible inside here? M1 of Z. That means you have to have a matrix whose entry is also integer. Then you have to get this. Do you think it is invertible? It is not, in fact, invertible. I am very sure it is not invertible because this one and this one, right, gives you 4 as a determinant. The 4 is not an invertible element. So it is much more. So can you see the perspective? From the school level, we always work on the field, so it is easy. Every non-zero element is invertible, that is like implicitly assumed. So you can just go and say that, okay, I will check the determinant. If it is 0, I'm not going to work on because it's not invertible. If it is not 0, then I will work on. Yeah, it is okay in the school level because they will work on field. But in higher level, it is not okay. Even though the determinant is not 0, it is not sometimes. So the correct thing is that inverse exists if and only if determinant, the value, the amount in the underlying ring is also invertible. It's an invertible element. So that is the way. Okay, remember that is the way. So similarly, we want to do something here. I wanted to see, since Z12 is very nice, I can just like write it 0, 1, 2 up to 12, sorry, 11. And it's like modulo 12 addition and modulo 12 multiplication. It's very nice, easy, I can see it. In algebra, seeing is the very important thing rather than abstracting. And I wanted to say something is invertible if it is GCD of that A, 12 is 1 or not. I mean, you must have seen this, but for those people who is not seen this, I'm telling them, okay? I'm just writing for them. You have to check the GCD against 12. 12 is a fixed. So from this, you need to go and check the GCD. Exactly whenever it is 1, if only if A is unit. If it is unit, the GCD will be 1. The GCD is 1, is a unit. And there is some beautiful mathematics hiding in there. You have to prove them and understand that, okay? But on that perspective, you can see that 1, 5, 7, 11 are the exactly the real thing, okay? And also, because of number 3 little bit connection, one can see that the counting of that is nothing but called Euler-Torschian function, which is 4 in our case. So generally, Pn is counting A such that GCD of A and N equal to 1. It's a counting. So one can see that. So it's a determinant function. Determining is a determining. The torsion function is giving you the number, and it's a determining. You have to check is it GCD 1 or not. Okay, this is also pretty basic. Okay, another basic thing. I am sure I never seen this thing in my master's level. Look at this. F of x belongs to the integers polynomial with f of 0, that's okay. Like when 0 takes 0, the 0 becoming like a root, that's okay. This kind of ideal you can see that. But I'm saying it little different here. Congruent mod 3. That is, whenever I'm putting f of 0 and that element divisible by 3, there is a two condition, not two condition, in a way that when f of 0 is 0, then it's a normal thing. But I'm saying that f of 0, it is a multiple of 3. I'm collecting all the polynomials. Prove that that is an ideal. How do we prove that is an ideal? Direct way of proving. So there is a beautiful way of proving which is indirect, but there is a direct way of proving. Use this, okay? How one do prove? All I want to show that it is closed under addition and observes the ring. Okay, closed under addition easy from here. You take f and g, point wise it is closed under addition, and f, g, hf, h is the outside one. When you put this f, which is inside, it is a multiple of 3. So everything is multiple of 3. Once is a multiple of 3, everything is multiple of 3. And the commutative property says that it's a two-sided ideal. Okay, whenever we talk about ideal, we always talk about two-sided ideal. Okay. So this is the example we already talked about. 0 is the prime ideal of Z. It's an integral domain and it's not a maximal ideal. Why? 0 by this one. Again this, which is an integral domain. So it is prime, but not a field. So not maximal. Another direct way of saying that every other ideal contains 0. In fact, not only 2, but you can see that there is a strictly a different ideal between 0 and Z, which is 2. In fact, 3 is there. In fact, 4 is there. In fact, every other ideal contains 0. That's why it is not a really a prime ideal. Sorry, maximal ideal. Okay. Now we are level up. So some of you already did these things. You might have faced this, basic questions are basic, but really basic questions are put in a way, such a way that our brain get confident and enough warm to go for the next level. Okay, let's go for the next level. And I'm telling you, all these 10 problems are very important to solve next 5 problems. Okay, all these 10 problems really enough. That's how it's maintained. Okay, the evaluation map. So the idea of the question, not the solving, the idea of the question actually giving what is the notation, basically introduction of the notation. EV2 means the evaluator 2. So it's an homomorphism from Z. In fact, from any ring, and you take A belongs to the ring, from the polynomial ring of that ring to here, EV at A is nothing but F. Is take the F at A. It's called evaluation map at A. You can change a lot of these things are going to come in future. You will see that especially in functional analysis, it has a very depth connections. Okay. So the statement is the problem 5. The evaluation map evaluated true. Prove that it's in a ring homomorphism. Determine its kernel. Right. So routine check will prove it's a ring homomorphism, and you can see that EVAF actual definition. Sorry. F of 2 equal to 0. So basically, I'm collecting all F from ZX such that F at 2. And you can see that I'm collecting the another way of putting this ideal. Basically, it is an ideal, kernel or ideal. Another way of putting this ideal, all polynomial which has a common 0 at 2 or common solution at 2. I'm collecting all those things. Especially, of course, 0 will be there, but I'm interested in this x minus 2. The x minus 2 is going to be there. Here I had written the kernel is generated by x minus 2. So far I know when I replace like EV of x minus 2 is 2 minus 2, which is 0. So from that I can see that x minus 2 is inside the ideal. But how can I prove x minus 2 generates this? That's okay. Kernel of EV. But how can I prove this is equal? Any idea? I wanted to prove x minus 2 is entire of that thing equal. How do I prove? How can I prove? Any idea? Think about little bit. To prove something, we need to take something here, no? Let us take f. Let us take f. I know f of 2 equal to 0. This much I know. From this, how can I prove this f looks like x minus 2 into something? How do I know? Shall I prove? Shall I prove?
Yes, sir.
Okay. It looks rather very simple, but the argument is very important. Let me prove step by step. I will take f from the kernel of EV2. I know this fact, f of 2 equal to 0. This much I know. But remember that z of x not ED. Remember, that is one of the very, very important fact. This is not an ED. This is not an ED. So how can I proceed? This is not an ED, but still we can proceed.
Using factor theorem?
Yeah, that's the thing. No, it is not ED. Can I use factor theorem till? Still, that's the question. That's what I'm trying to say here. Factor theorem, you are trying to use the division, right? Basically, what we are trying to say using factor theorem, f of x going to be a q of x into x minus 2. I'm going to divide by this. Then there will be some r of x. And I know f of 2 equal to 0. And this is equal to 0. And this is equal to 0. Before even that, before even going to that point, what you can do actually, this r of x, right? This r of x, degree of r of x must be less than degree of x minus, strictly less than. And you know that this is like 1, x minus 2. So it must be 0. And you sure that r of x equal to some constant, let's say c, some constant. In that sense, f of 2, q of x 2 minus 2, q of also 2, sorry, 2 minus 2 plus r of 2. But that's a constant, so I can put c. And this is 0, I know. This is I0, no? I know c equal to 0. The moment I know c equal to 0, this part is not needed. I know that f of x is actually q of x into x minus 2. This is the beauty of the factor theorem, but it will work only if it is an ED. But I'm sure it is not an ED. Because every ED is a PID, I know it is not a PID. Then how can I proceed? Do you see that even a simple problem like this, having a lot of reasoning, sometimes the over knowing will lead us into different way. Basic, see, so I'm telling you, this is a point, great point to tell. This is true. I'm not saying it is not a true. The claim is true. But the reasoning may not true. Most of the people will have the reasoning, oh, it is easy. Okay, divide by x minus 2. We will get quotient and the remainder. Remainder degree must be less than 2, less than 1. It must be 0. Then it's a constant and we will prove the constant is like this. Can I use the factor, that idea? Because it is not ED. Hence it is not PID. Can I use the factor? So even you see there is a simple question like this. It takes long triggerings. So I will let you to think about it. I'm not going to solve this. You have to go little deeper to understand. If something is wrong, you have to come back to me. Now I'm posting the question here deliberately. Is this true? My question is my question is clear? My question is clear to you? Definitely kernel contains this, I'm sure. What about the reverse one? And I know this is not ED, remember. Is my question is clear? Please somebody clarify. Or otherwise I will put it in another way. Clear? Very simple question.
Other way.
So basic question is, forget about this statement. Kernel of EV2 contains the ideal generated by x minus 2. Basically x minus 2 is inside because 2 minus 2, EV of x minus 2 is nothing but 2 minus 2, which is 0. The question reverse is true. Is reverse is true? Somebody gave an idea. Can we use that factor theorem? You can use, but in what cost? Are you assuming this is an ED, which is not a ED? In fact, I will tell you one of the very important results for CSIR. Result or fact for CSIR, R of X is ED / PID if and only if R is filled. If and only if. This is if and only if. It's ED or PID if and only if R is filled. Of course, I'm assuming R is an integral domain. Minimum R is an ID. That I'm assuming. Commutative. I'm assuming R is ID. After that, R of X is ED / PID. Anyone. ED implies PID. PID is also okay. If it is PID, then if and only if R is filled. If and only if. That's why Z is not actually a ED. So now I'm asking the calibrity of this question. Is it true that kernel, whatever I'm written here, or did I make deliberate mistake for you to read the notes and find out? Right? So yeah. Can you see even the next level we are having a problem? Let's go to the next one. This is a very nice question. This is a really a nice question. Similar to that. Why it is similar to that? Yeah. The question is, I have a Z, then I quotient by X. Is it isomorphic to Z? Something like this in group theory or ring theory, even many other places of algebra, somebody asking this question. Okay. The best way to do, I will post one question in NBHM similar to this. S1 is a circle, complex number with modulus 1 divided by plus or minus I. Sorry, so let me put it. The similar question in NBHM, S1 quotient plus or minus 1 plus or minus I. Isomorphic to what? This is the question. If somebody asking such kind of questions, the best way to do it in the case also, Z of X to Z, define a morphism. And in our case, it's EV0, Z of X to Z. Then look at the kernel. These EV maps are homomorphism, ring homosome. Look at EV0. Set of all x such that f at 0 equal to 0. I'm collecting all the polynomials which is 0 at 0. Of course, x is going to be there. Of course, the ideal x is generated is going to be here. Kernel of EV0. Again, the same question. Why it is true the reverse one? That means you have to take a polynomial here, f. Then you have to show that f looks like x into some gx. That is fairly easy. I will tell you how to do that. Shall I do it? Shall I do it?
Yes, sir.
That's fairly easy. I will tell you. Because I take a f from kernel of EV0. Then how do the f look like? This is what I'm trying to push you. How do they look like is the most important question in the exam. an x power n, correct? Plus an minus 1 xn power minus 1 plus dot dot plus a naught. And each an minus 1, everything belongs to z. I know one fact. What I know? This which I know. F of 0 is 0. So f of 0, everything becomes 0, which is 0. Everything will become 0, a naught. That means a naught is 0. If a naught is 0, then f is what? F of x is nothing but an x power n plus an minus 1 xn power minus 1 plus a1 x. Now you can take x out. You can take entire x out. Then an x power n minus 1 plus data plus a naught. That is my g. So x into g of x. Is it clear now? In this case, at least, right? Am I right? Is it clear for you people? Now, if I take an f from here, then the f looks like x into g. Just because of the a naught is 0. That is the idea. Now the question, can I use the same trick here? The above one. And it has not, I am using no fact of ED, divisibility, blah, blah, blah thing. So I'm coming from the first principle. Try to solve as basically as possible. So this class, good. That's why you have to attend this kind of classes, okay? From the experience, people, this is coming out of my experience. I have a lot of teaching experience, okay? You might know, okay, if you're, for example, you are in the interview, people asking this question, some people will have a overconfidence and say, yeah, do this, do that, you will get the idea. That's it, like that. But you have to go with a proper reasoning. There is a beautiful statement in mathematics. If you want to learn mathematics, you have to do the mathematics. And which is true. I know it is true. Okay. Shall we go to the next problem? Shall we go to the next problem? Somebody, are you people typing something? I'm not able to see. Some messages are coming. Some type.
Yeah, Jay, they are reacting. When you are asking this, yeah.
How to see the reaction somewhere?
See, I think it is available on the screen, but as you are in the
Oh,
presentation,
sharing.
may not be. Yeah.
I understood. Okay. Now you try to understand problem 6. Can I use the somewhere the same thing to problem 5? Try to apply, try to think without using ED. Never go for ED, equivalent domain. That algorithm is not really available. And also, I will give you one more thing. In ZX, 2, x, ideal generated by 2, x. This looks like fx 2 times fx xm gx. Okay, such that fx and gx belongs to zx. Try to prove within this side. It is not singly generated. You cannot find a polynomial hx which singly generated. Okay, try to understand that. If you start working on that, you can understand what I'm trying to say. The ED is not possible, PID is not possible, still something is possible in this. That's why Z of X is something one can really go and do research. Okay, let's come back to problem solver. Zero divisor in the quotient. Okay, look at this. X square minus 1, I can split into x minus 1 into x plus 1. That is one of the advantage. And because of this splitting, the quotient having a lot of problem. Not only that, look at this. 2 into 3. 2 is not a 0, 3 is not a 0, and 2 into 3 actually becoming 0. So determine this particular element, 2 power plus 3 power x, a polynomial of degree 1. Inside this quotient, whether it's a zero divisor or not. Okay, we like to ask this question whether it's a zero divisor or not. And I written entire solution here. For time being, let me go to the next problem, because I don't want to do this. Is a very big problem. If we have a time, we will come back. Let's go to question number 8. X square plus x plus 1 is irreducible over z to x, and describe this one, the quotient. Whenever degree 2, degree 3 is very nice. Okay, what is the reducibility? If the higher degree polynomial, I can break into 2 lower degree polynomial, then I call reducible, right? But degree 3, degree 2 is very nice. Suppose I have a f of x and it's a degree 3 or 2, then 2 other degree, it might be 1, 2, or 2, 1, or 1 into 1 into 1. This is the way I can split. If it is a degree 3, 2, 1 is a possibility, or otherwise 1, 1, 1 is a possibility. Because of the commutativity, I can think of. If it is 2, 1, 1 is the only possibility to break it out. In other ways of saying, whenever there is a linear, so 1 degree, the degree 1 polynomial is called a linear polynomial. Whenever there is a linear polynomial, basically saying it has a solution. So that is the one thing you have to understand. Checking this irreducible, if it is degree 3 or 2, is very important, very simple to check whether it has a root or not. In Z2, we have only 2 elements, which is 0 and 1. If I put 0, 0, 0, 1, not 0. If I put 1, 1, 1, 1, which is 1 plus 1 plus 1 equal to 3. Mod 2, under mod 2, it is actually 1, not 0. So that's why it is degree 2 without a root. So it is not a reducible. It is actually irreducible. And I said, if I have a irreducible from field, remember later on you will see that these are field F2, ZP, okay, FP, those are field. Then f of x is field because it is maximal. I said as a fact. If you are right now understanding, these things like an undergraduate, take this as an information. If you've done undergraduate, I'm sure that you must have come across this fact. I'm just putting together. But if you are like first year or second year of undergraduate, you may not know. Take this as an exam, like information, so that in the class you can relate it. Now we are entering into a very beautiful problem. This is again intermediate level drill. This is not a basic problem. So units of Zi. So Zi is a ED actually, because it has a norm, the Euclidean norm, all these norms. So if alpha is one element and beta is another element, if I multiply alpha into beta 1, if I'm getting 1, that's what we say unit, no. And the norm defined for a typical element A plus IB looks like A square B square. And you can work out little bit, understand that whenever there is a multiplication, you can understand that this is also multiplicative. N of A, N of B. That is something special about this. What makes, let us ask this question, okay? If you really wanted to do algebra, one of the very important question you should ask, what makes some example unique? Let me post one question in a group theory. What makes Q8, quaternion group of 8 or 8, something unique? Which makes it unique? I will tell you which makes it unique. It has exactly one element which is order 2. That is a unique property. Out of that property, you can get it. What is the nicer thing about that? Every subgroup is normal. Every proper subgroup is cyclic, but the group is not a abelian at all. It is a non-abelian group. But every proper subgroup is normal. Every proper subgroup is cyclic. Every proper subgroup is abelian, but it is not. So those are the key factors. Even though those are the key factors, still you can see that the uniqueness of this group is it has a very unique one element which is order 2. No, none of the other element of order 2. Everything is order 4 other than that, except the identity. Identity is 1. Something like that. What makes it unique? This is one of the property makes it unique. Okay, try to understand these things. Okay, now we are trying to prove the units of this one is exactly plus or minus 1 plus or minus I. That's it. How do I prove it? So basically, you take alpha, like, see, this is a, if alpha is a unit, then alpha into beta, n alpha into beta is 1, n beta, and that is equal to 1, n of 1. But n of 1 is like 1 square, that is like 1. So that says that n of alpha into n of beta equal to 1. That implies n of, like, norms are positive. That always goes into this n natural numbers. If you irregulate 0, that means throw away 0. Read the proper definitions. Okay, I am not able to give you because of the time, but try to read the proper. The norms are positive integers only. So that says that n of alpha is 1. So what is n of alpha? Alpha equal to a plus ib. N of alpha is 1. That is a square plus b square. But a and b are integer. A square is a natural number, then b square is a natural number, maybe 0 possibly. So a square plus b square may be whole numbers, natural number union 0, 1. That implies it cannot be a and b, must be plus or minus 1. Correct? If it is not more than 1, sorry, not plus or minus 1, then a square will go much more bigger number. Minimum 2, right? So using that idea, one can see that a and b is plus or minus 1. The very important fact you have to observe this multiplicative property. This is something you may not get it in many places. This multiplicative property is very important. It's very kind of unique. I will not say exactly unique, almost unique to this Gaussian integers. Okay, maybe you can go to the very good AI and ask what are the unique and natural properties of Gaussian integer, and it must be the one. I guess. I don't know, but you can try. So let's go to the main problem. Before going to the main problem, the final problem. In a PID, okay, in a PID, what is a PID? Every ideal, if you take an ideal, then it's generated by a single element. What is that? It is R A such that R belongs to R. You can relate with the cyclic groups, basically. Cyclic groups are just basically what is cyclic group? If you catch one element, you can catch everything. Something like that, okay? So in a PID, or if I equal to generated by element and j equal to generated by element, I plus j. What is I plus j? I plus j definition is a plus, so basically x plus y such that x belongs to I, y belongs to j. So we are going to say this is a GCD. It is generated by another single element because it's a PID. It is generated by A, it is generated by B, then it is generated by something related to AB. Something related to AB. Okay. Am I still visible? My screen is visible. Some call coming and disturbing me.
Yeah, yes, Jay.
Yeah. So basically, what I want to prove, you start with the D. Again, this question is meant to conceptual. I written here conceptual. Conceptual means trying to introduce the notation. So D is the GCD. GCD means greatest common divisor of A. Define up to. Sorry. Defined up to the unit. This you have to understand. In the Z, is different. Okay. In the Z, the definition of GCD is different. What is the definition of GCD in the Z? I have a two integers. Then I will say it is a positive number, positive natural number, basically natural number, which divides A and B. In that way, we are just, throwing the concept of negativity, right? Throwing the concept of negativity. But in the PID, we may not have an idea of negativity. How do we say something is negative? We may not have a concept of negativity, right? So that's why there is a refined definition that you should see. There is a refined definition. Please refer the standard books. Okay, lean on the standard books. Basically, which is D divides this, and define up to a unit means you can allow the unit, you can throw away the unit, basically. Okay, but this is the actual thing you need. The ideal generated by A inside D, why? Because it's dividend. The ideal generated by this is inside D because it's divides. Okay, D divides. So that's why I is there, A is there, B is there. So this inequalation is okay. And this is the one of the very important thing you need to observe. This is the theorem or proposition, whatever. Every greatest common divisor can be written as linear, combination. RA plus SB, combination. RA plus SB. Everything is a combination. If you look for A, so that's why defaultly it's in I plus J. Proof of this little hard, but for the integer case one can do. Okay, little hard to understand in the level of PID. But I wanted to understand this way. I really, for this question, introduction of this concept, not proving. Okay, that's why it's a conceptual drill. What you have to take from this question is every greatest common divisor is a linear, the combination of AB. That's what you need to know. Okay. Now all these things are done. Now we are really going into this graduate school problems one by one. And it will be nice if somebody reading it. Okay. Can somebody read it? Someone read, please.
Every maximal ideal of a commutative ring with identity is prime.
So what is true or false? Any? So I don't want you to give me the answer like in the sense of you have to reasoning. Before answering, you can take the idea. So what I'm trying to say, look at the question. It is basically true or false question. You can say true or false like that. Like you take a choice, may not be correct. You may be correct, you may not be correct. Once you take the choice, for example, true. If you take a true, you may be correct, may not be correct, 50-50 chance. But what happens that if you take the choice, then start reasoning it, you may get the correct answer. That's okay. If you are correct, you are correct. Your intuitions are right. If you are wrong, you will get the idea that you will wrong. Then your intuitions will change, and it will be easy in later. That's why I want you to take the choice. So you can take a choice. You no need to tell. Take a choice if it is true. So if I am going because of my knowledge and other things, I will say that it may be true, maybe false, but let me take for true. But we know. Look at the keyword maximal ideal commutative with ring identity. We know one thing, R by I is field if and only if I is maximal, and this is ID if and only if I is prime, and they are connecting prime and maximal and commutative ring, so that must be like this. But I know every field is ED, so that's why it is true. The quotient characterizes maximal if and only field, prime if and only if integral domain, shows that field integral domain are track saying about the ideal. So remember the comment, the non-converse keep it true. That is, the converse is not true. If you change this place into prime, this place into maximal, it's not true. That's what I have written. So it is true. Okay. I gave the proof of that. Okay, let's go for this. Read the next question.
There exists a non-zero ideal I of Z of I such that Z of I over I is infinite.
Right. There exists a non-zero ideal in Z of I where this is infinite. So very nice question. Very simple, easy to understand. They're saying that is there exist. So we can take in a way. It's true, maybe. It's maybe false. But what I know about Zi, this Zi, right? I know some of the thing. Like for example, plus or minus 1 plus or minus I is actually the thing. And it's suggesting me something about this is a finite. It has a finite units. So if it is as a finite units, what happens to the thing? It is like PID or ED. It has a ED, no? That alpha is A square plus B square. These are the things I know. And that actually helps us to understand this. So maybe I can take a choice. So if I go for finite, what happens? If it is true or not, like I have a non-zero ideal. Of course, zero ideal, you will get the same thing. Right? You will get the same thing. So let's go with a non-zero ideal. If I have a non-zero ideal, it is going to be infinite or not. What is my choice? I will say it may be true, it may be false, but let us take true. And I will try for some time. Initial analysis, it is an I know this fact Euclidean domain and it's a PID, everything is just generated by 1. This much I know. And what is Z I by this alpha? What is alpha? Alpha is some A plus IB because singly generated PID I know. So I have this and A square plus B square not equal to 0. Sorry, not equal to 1. That is a very important information. If A that is equal to 1, that says that it's like a invertible. Once it is invertible, things are little crazy, you know. Things are getting crazy. It's a whole and it will collapse into 0. Okay. So if it is a finite or infinite, how can I proceed? I'm just thinking slowly. But I have to say this somewhat suppresses the things plus or minus 1 plus or minus identity. The units are like finite. So I will go with the finite. Okay, this statement may be not true. How can I proceed? This is the way to proceed. Look at this. A typical element of this one looks like beta plus ideal alpha. And in fact, in this beta, I can choose something nicer. Remember, alpha is not equal to 0. Remember, something nicer, I can divide. This is ED. Some quotient alpha plus gamma, where the norm of gamma less than norm of alpha. And beta minus alpha q equal to this gamma. So instead of choosing this one, random beta, I can choose that gamma such a way that this gamma is a matters, okay? It's less than alpha. Remember, this is one of the very important thing. First, I have a representative for any beta. This one divide by alpha, you will get this gamma by n of alpha, n of r. And in the cosine representative, I can choose beta, but I can leave the beta. I can choose r because beta is a part of quotient of this. This is reducing under modulo. If you go for add alpha on this side, the alpha part will go down. So the beta plus alpha is same as gamma plus alpha, ideal alpha. But what is the advantage? The norm of this one is less than norm of alpha. But norm of alpha, what is that? A square plus B square. Right? A square plus B square, which is the finite number. Which is the finite number. So how many gamma I can choose? such that norm of gamma bounded by a square plus b square. So that means it is a finite, no? That is a uniqueness I want you to understand. Go to the internet or somewhere, you can understand this norm function is very important. The quotients are bounded by the norm function. It is either 0 or this one, which is less than. That's why it is like that. Okay, it is bounded. So basically, I written a square plus b square for alpha, but when I was writing the solution, I didn't write like that one. I said that any gamma a square plus b square, which is bounded by norm of alpha. So norm of alpha is finite, and this is a positive number. So you can get a finite number of choices only. You cannot get an infinite number of choices for alpha. The quotient, the representative n. So hence it is a finite. This is one of the very toughest problem. Really toughest problem. And I'm sure that I did not get the answer until I see the answer. I tried to do it. I'm not getting the answer because I was missing the property of norm. I didn't get it. I went to the internet, searched for the answer. Okay. If you don't get it, it's okay. You just go and understand it. But one thing I get it from the internet more, the extra observation. Look at the observation. If you have the ideal n, this Zi quotient by I, this is basically n. This size is n square. The more you go higher, this is also higher. That says something about this n. If you choose n is more higher, the ideal is smaller. When the n go higher, the n generator ideal goes smaller and smaller. That evidently catched by this number. We have a feeling here. We can prove in fact, but you can see that. Can you give me a ring of n square? Somebody asking, okay, can you give me a ring of like 9? You can give, okay, go Z9 is there, right? Z9 is there. Now compare the Z9. Is it isomorphic to Zi by this one? Is it true? That is a question I'm posting. We know Z9, correct? Is it true that Z9 isomorphic to Zi quotient this one? It is a very interesting question. Okay. As I said, I don't know the answer for the question. I went to the internet, observed that, but I got an extra observation. Okay. There is a word I put it, lattice intuition. Lattice intuition means when the n goes higher, this goes lower. The size of that's what I put it, lattice intuition. Okay. Let's go to the next question. Problem 13. An exponential polynomial. Okay. Can you read this one? This is a very beautiful thing of Einstein criteria. Somebody read it?
The polynomial p of x is equal to 1 plus x square by 2 factorial plus x power 101 by 101 factorial is irreducible in q of x.
Okay. So the question is clear. Let us look at the question. Before true or false, let us look at the question. What are the elements of the question? Have you seen this kind of polynomial somewhere? Do we seen this somewhere? Have we seen basically something like this? 1 plus x square plus 2 factorial plus etc. plus x power 101 by 101 factorial plus etc.
So is it the expansion of e power x?
Yes, it is actually a part of expansion of e power x. Exactly. So that's the first thing we need to know. And the second thing we need to know, it stopped exactly at 101. What do we know about 101? Do we know anything about 101? So the 101 is a prime. That is another thing. So this is one of the beautiful example where Gauss lemma and Einstein criteria we can put together. So let's understand the simple one. The Einstein criteria, suppose I have a power n, x power n plus dot a naught inside Q of this one. Suppose I am able to find P that is not dividing AN, but it's dividing a n minus 1, a n minus 2 dot 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 up to a naught. Remember, up to a naught. And p square does not divide a naught. That implies, so let's call p of x. P is irreducible. So Einstein's criteria says, can you able to find a prime number which does not divide the leading coefficient but divide every other coefficient, right? And p square, when you go for p square, that is not dividing the constant term. So basically, the one is not allowed here. That's why we need some other techniques for dealing with the one here. In the case here, the polynomials are fractionated. But there is one simple trick. Can I multiply the polynomial just by 101 factorial? If I multiply to 101 factorial, what happens? I will write in a reverse order. I will write this in a reverse order. I have a x power 101 plus something 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 plus 101 factorial. I have a new polynomial px. The leading coefficient now is a monic. The leading coefficient monic. I have a new polynomial. First, you have to convince yourself if the new polynomial. What is the new polynomial? 101 factorial px. This new polynomial. We have a new polynomial. If this polynomial is irreducible, is that is showing automatically this is irreducible, or this one is irreducible? If this showing is irreducible, basically I'm asking the question, f is irreducible, suppose. Then I am multiplying some number c, f, is it irreducible? If this is irreducible, is this irreducible? Try to convince yourself. And it is true. I'm telling you it is true. Okay. Try to convince yourself. So that's what I'm doing. I don't want to work on the things. The school level, you have to have, you are having a technique called conjugation technique, right? Suppose I minus 3. Find the inverse or something. People will go, okay, I plus 3, I plus 3. Why I am doing this is called rationalizing the denominator. We don't want to work on the denominator with the I. We are trying to rationalize. We are trying to get rid of the I by doing so square also. Square roots also we don't like. We like to work on the squaring and doing and want to come back. Those kind of things we do. The same thing I'm doing. Let's multiplying. Look at this polynomial. Now this polynomial looks nice, and 101 is the point. This 101 is there, right? This 101 will not divide this, but will divide everything, including, but 101 square will not divide 101 factorial. That you have to understand, okay? Because 101 square will first the 101 divide 101 and will remaining 100 factorial. Then 101 will not divide the 100 factorial. All other numbers are less. It cannot divide. So from there you can see that this 101 works. But why should I use the word Gauss lemma? Passes between z of x to q of x. So this Gauss lemma saying something. Let's go back to that. Today class somewhat patchy, but it is helpful. You have to see. Okay. Gauss lemma saying primitive polynomial irreducible over set of x remains irreducible over q of x. Primitive means like 1 in the coefficient. I'm saying like the leading coefficient 1. So something you can prove using Einstein's criteria that you can prove you in Z. This Einstein criteria works for Zx, not other than that. Okay, it is works only for Zx. So in this question, what is the technique? The technique is first you have to realize changing this. Where is that question? First once again. Okay, where is the question? Realize that you have to change that to like this by multiply and get a monic polynomial, primitive polynomial basically. Primitive polynomial in the sense all this coefficient, if you take the GCD of the coefficient, it is 1. Because of this is 1, everything will turn into 1 GCD, okay? So that's why it's an easy thing. The Gauss lemma works much more general framework, primitive, but we have 1, so the GCD, if you take a against of anything, that's going to be 1, so we don't have a problem. And now we choose 101 which satisfying Einstein's criteria that shows that this polynomial actually irreducible. If this polynomial irreducible over this one and a primitive in the sense of Gauss, then that is going to be irreducible over this, and the change of thing will not apply, of course. So this is the thing you need to develop, okay? Here I am not giving the solution, rather I am giving the solution. What I am doing actually, I am giving the plan or pathway to understand what you have to do for this kind of question. First, try to understand what if I change it like this. Suppose another question I can ask, f of x is irreducible, suppose. What about f of x minus 2? Is it irreducible? Why not 2? Why not some r? If f of x is irreducible, what about f of x square? That is not true. For example, f of x is just x, but f of x square is just x square, which is x into x, which is reducible. So this kind of question you start asking yourself, you will develop the idea. So that's why this question is very beautiful thing. And one more important, so that is what I written here, the example. Gauss irreducibility says that irreducible in q of x. If you really wanted to irreducible over q of x, better to come down of z of x and work with the Einstein criteria. You can come down and go back because of Gauss. What Gauss saying that primitive polynomial. Primitive polynomial basically take the coefficient GCD of that coefficient is actually 1. Then it's called primitive polynomial. But one of the coefficient is 1, GCD is going to be always 1, that's okay. So one more fun fact is that this degree 101 truncated, somebody guessed correct, we have a e power x, degree 1. Now one can ask another question, what about this polynomial? X square, sorry. Is it irreducible? Should I go, if you able to understand this thing, should I go up to 1 plus x plus 1 factorial, x square by 2 factorial, x power phi by phi factorial? Try to prove this. Okay, if it is the thing, then why not general n? Can I stop in the general n? 1 plus x by 1 factorial plus x square by 2 factorial plus x power n by n factorial. These are called a truncation, no? It's if you go for trial series kind of idea, it's called fnth coefficient. The nth coefficient, is it going to be irreducible? If you are able to do at least for this level, it will be nice. You have a very nice set of polynomial. For each prime, you got a polynomial, no? Then multiply by phi factorial, you can get a nicer polynomial which are irreducible. Okay. So the next question, somebody read it. Anyone?
If R of x comma y is a principal
If R of s comma y is a principal ideal domain, then R is a field. Before proving this theorem, let me tell you again the fact. R is ID minimum, okay? R of x is
ideal domain, then R is the field.
yes. One of the important result, try to remember this. R of x is ED or PID if and only if R is field. In that case, this question is correct, but it doesn't make sense. This question is correct because R of x of y, actually R of xy, the right definition. R of x comma y is this one. So if it is a field, that is implying this must be a if it is a PID by this theorem, this one is a field, but that is not true. That is not true at all. That is not true. There is no inverse of X inverse, no concept of X inverse here. Here we have a concept of X inverse. So from here, there is something called round bracket. Round bracket is a concept of some device or fraction field. Every integral domain can be completed by fraction field. Okay. For example, Z. What is the smallest field containing Z is nothing but Q. Similarly, every integral domain, if it is not a field, you can able to complete into field. You can throw that into some minimal field. Some way it is a minimal field. Those are called a fraction, field of fractions. Okay. So in this case, what they are asking, the question is correct, absolutely correct. But this result clearly saying that such a situation not going to happen, because you have a two variable. The actual algebraic definition of two variable is this one. So if it is PID, then this must be field, but which is not true. R of X is not field. There is no concept of X inverse in this thing. How can you represent X inverse in terms of polynomials of X? That is not true. Okay. It's not true. Okay. Now, okay, let's go. But anyway, the question, whatever they're asking, it is a no evidence, but still theoretically correct question. They're asking R of XY is a principal ideal domain, then R is a field. Use this. What it is saying? R of X is ED or PID. Then R must be field. This is the result. So we apply to that case. R of X is ED. That is R of X of Y. This is the way two variable goes. Then this is a field. If it is a field, every field is a ED, hence PID. So R of X is field implies PID. That implies R is a field. This is the proof. But that is not like, it's not true. The side note is even for F field, F of XY is not PID. Remember, it's not never extremely restrictive. The hypothesis is extremely, this is not true. Because the moment you go from F of X to F of X, this is PID, not field. It will be fun fact why the X inverse not inside F of X. I will give you the hint, try to prove. Suppose X inverse inside, that is also polynomial of X, no? X inverse, suppose some F of X. Then X into X inverse, that is 1, that is like X into F of X. So this is a polynomial, this is a polynomial, you are just multiplying. What happened to the leading coefficient? If the leading coefficient is n, then leading coefficient when I multiply, it's going to be n plus 1. But degree of this is 0. Degree of this is 0. Degree of this is at least 1. That's a contradiction. So you are not going to get the X inverse, okay? From the beginning of this class, I'm stressing one thing again and again is, how do they look like? Okay, that is one of the important things. So here something is there, it looks like this. Okay. The last question, I wanted to leave this last question to you people. Clearly the solution written, which is very easy. It is again some kind of idea of, I will tell you what is the main motivation of this idea. How many of you know root 2 is irrational? Proof. How many of you know this proof? How do I prove root 2 is irrational? Any idea?
So there's a method we learned in, I think, 10th or 12th.
Same. That's what I'm asking. That is the same method you have to do. You see, something similar. So basically, the 10th, 12th method is like you have to go by P by Q, where P belongs to Z, Q belongs to natural number. GC of P by Q is equal to 1. Then square it. 2 equal to P square by Q square. Then 2 Q square equal to P square. That implies 2 divides P square. That is P dot P, correct? Then 2 divides P we know if AB, a prime number divides AB, then it's AB. So it's A and B is same. So 2 divides, then it can be written as 2 into alpha. Then I'm projecting here. So 2 alpha the whole square equal to 2 q square, which is 2 into 2 alpha square, 2 q square, 2 will cancel. That implies 2 will divide q square. That implies 2 will divide q. That is a contradiction because I assume the GCD is 1. Here 2 divides this one, 2 divides this one, which is a contradiction. That is the same thing you have to do here. That's why I don't want to give you the answer. But let us understand the question. Let R be the commutative integral domain, okay, ID. So this commutative is not needed. Integral domain means it's always ID. ID, integral domain, and suppose AR means ideal generated by R. This is the ideal generated by this thing. Why I am using the same different notation? Because it is given in the question. In this question, that's why I'm using. It's basically A generated ideal, B generated, and I'm taking the intersection. That is AB, the ideal generated by AB. So then if I have a generated ideal, B generated ideal, I'm taking the common intersection. Then it is a AB generated ideal. Then A and B shares no common divisor other than unit. Okay, there is a word. In fact, let's give you one thing about a thing in Z. Okay, I have a A, I have a B in Z. Then AB mod is LCM of AB, GCD of AB. That is the exact statement is there. You must have learned this from your introduction to number 3 or not. If you don't know, understand this. Mod of AB. So I just wanted to take the sign. Just the numerical value of AB is nothing but LCM of AB, GCD of this one. When this LCM exactly equal to AB, assume that you are in the positive part. A is greater than or equal to 0, B is greater than or equal to 0, AB equal to LCM exactly when GCD is 1. Instead of saying GCD is 1, because as I said in Z, we always take in the positive format, the definition of GCD little rigged, or otherwise I will say little modified because of number 3. In algebra, pure algebra, that is not the definition. That's why the word other than unit. No common divisor other than unit. Okay. The real thing, what we say actually common divisor for A and B. Suppose in a PID, I have a PID, okay? Then I'm going to define what is the definition of common divisor, right? And the greatest common divisor. To do the greatest common divisor, we need some kind of a comparison, but common divisor, let me do the common divisor. I will take A generated ideal, I will take a B generated ideal, then intersect it. Since we are in PD, the intersection is generated by some other element, no? There may be many elements, I don't know, but I know there will be one element because of PID. That is a common divisor. So there could be more common divisors. To define greatest common divisor, we need to go one more step. So that is you have to go and learn it, okay? So from here, at least you try to understand the definition for used in common divisor, greatest common divisor, which are very much modified for Z. And in our Z, we have a concept of positivity, negativity. We have a concept of a nicely positive number, negative number, nicely arranged. But that may not be true in general. So that's the first thing you need to understand, that really we wanted to do algebra, not number theory. When I was a student, I always ask this question: what is the difference between the algebra and number theory? Everything like coincidence, but there are lot. There are lot and lot. Okay. So let me stop my class here. But I gave the essential idea. After this, I just put some quick references and pitfalls, some of the pitfalls, right? This is the one thing we need to understand. Z of x is not PID. That's a common thing you should know. And one of the common thing, 2, x is not a principal ideal. You should know this proof, because I know at least 5 students, they have been asked this kind of examples during the interview. And this one, I wanted to warn this. The question they're asking is right, but this is never going to happen. Even it is a field, this is never going to be PID. Okay, but this is going to be UFD, always UFD. that a heritage pauses. And yeah, these are the thing I written some of the things you can go through in the notes. Okay, so yeah, let me complete this class. I created one Zoho mail especially for getting corrections when you feel something correction, or you when you need to like say something, sir, this is seems fair to add this concept in this thing. All the suggestion, all the corrections are welcome. This is the mail ID 𝐷_Jayakumar at Zoho mail.in. It's very specially for this feedbacks. Okay, you read the notes and tell me if there is a feedback. And I wanted to warn you, this is written by AI. There may be some mistake. Okay, so be careful. If you tell me, criticize me, I'm really welcome. So let me stop my presentation.
Okay, thank you, Jay, for this nice session.
Yes, sir.
Dear participants, it is your time to share your feedback. Feel free to share your comments.
Good evening, sir.
Good evening.
Sir, my name is Varada. So I have completed my BSc and right now I'm preparing for exam actually. But yeah, I'm just, trying to give an attempt at TIFR as well. So I found today's session like you provided the basic, like, the fundamental concepts about the ring theory. And I think the main thing which I really liked was the slides. It was like very well structured and easy to understand. So I think this is really going to be very helpful for the upcoming exam. So thank you so much, sir, for this wonderful session. And thank you, Vinod, sir, for organizing this class for us.
Thank you.
Thank you, Varada. Yes, others.
Sir, good evening, sir.
Good evening.
I'm Reshma, sir, final BSc Max students. Thank you so much for such informative and interactive section. The way you explain each concept step by step and made everything crystal clear. And I also got a clear idea about the difference between classical algebra and modern algebra. You explained it simple and effective way. Also, they share your own experience. It is enjoyable and raising question to think about that, sir. All the topics is very covered, very useful and easy to understand. It is truly wonderful and enriching section. Thank you, sir.
Thank you. Also, you tell us about which institute you are from. Whenever you say the name, like we come to know where are you from. Like,
Sir, I am Tamil Nadu.
which institute?
Annai Women's College, sir.
Okay, fine.
Correct.
Okay.
Okay, sir.
Thank you, Reshma. Others. So, dear participants, feel free to share your feedback. It will be really an inspiration for us to arrange more such sessions.
Right.
I am Dharmendra Singh from 𝐻𝐿. I am doing preparation for IIT-JAM and the TFR exam also. This class was very nice by Dr. Jayakumar sir, and this class was very useful for TFR exam and IIT-JAM also. I want to ask if I am unable to solve PYQ without books, any help, then what we should think within 10 minutes at home, and what ideas we can help if I am unable to solve a PY question.
Okay. You are asking
And,
about that
from the
what you
professor,
want to do.
Yeah.
Okay, I will tell you the
Yeah,
answer
yeah.
later. I will tell you the answer later about this.
Resources also. Resources also for ring theory.
Right,
Yeah.
right. Okay. I will tell you later. What others comments?
Hello, sir. Am I audible?
Hello, sir.
Yes.
Hello, sir. I'm Archana. I've completed my BSc from PHD Krishnammal College for Women from Coimbatore. Sir, I really enjoyed your class. My group theory is the only thing I'm a bit okay with. So ring theory, I was actually reluctant to start with. So with this class, it sort of paved a path for me to go in depth and learn. And you explained it in a very simple way with examples and like in-depth proof. Even if it's true or false, you explain the meaning behind why it's true, why it's false. So I really enjoyed the class, sir.
Right.
Thank you so much, sir. Thank you, Vinod, sir, for organizing the class.
Thank you.
Okay, thank you, Archana. Yeah, Supradeep Chandra.
Yes, sir. Am I audible now?
Yes.
Sir, due to some technical problem, I am not. I am unable to open my video. So, sir, I have enjoyed a lot because in the big catches you have not solved, but you have to put us in that way that we can solve by ourselves. That is the good point. There is one problem, that is modular and modulus function, and that is whose norm is certain less than certain number in the Gaussian integer, and there could be finitely many choices, so there should not be going to infinite.
Right.
That is a very good, and style of this approach is very good. I'm enjoyed a lot. Thank you, sir, and please provide study resource for the ring theory especially, because I am only to know the elementary level of ring theory. Okay, sir. Thank you, sir, for in this wonderful session, and thank you, sir. Thank you, Jayakumar, sir, for attending those interestingly.
Thank you.
Thank you, Supradeep Chandra. Any others? Yeah, I think many of them have left the meet. So, Jay, I think we can wind up with your comment to the question raised by Dharmendra Singh.
Okay, so in the level of modern way, okay, what I feel, this is the best thing happened in PhD. Nowadays we have a lot of AI tools. I don't believe AI can generate the solutions very nicely, because it can do. I want to say one thing. Today in Twitter, what happened? There was one picture of M. Karunanidhi, former Chief Minister of Tamil Nadu. But AI started telling me it is not Karunanidhi, it is MGR. And I said that no, it is not true. It is Karunanidhi. And started arguing with me. Gorg AI of X Twitter, okay. He started arguing with me, it is Karunanidhi. According to this, according to that, it is providing some kind of things. I was not able to believe. I posted this into my group, okay. So maybe I will send it to sir about this argument. This AI started arguing. But one thing is really working in AI, it can catch the searching. They made really well. The searchings are really well. So it is catching the thing. So if I wanted to learn really the ring theory, the best way I would say, for example, TFR and NBHM. First, I collect ring theory questions. I will try to solve it by myself. If I'm not getting, I will try again. Honestly, I will try again. If still I'm not getting, that's okay. I can go and learn. The best place to learn, actually, this math stack exchange, real humans contribution. Okay. But the problem with math stack exchange, olden days without AI, searching is not possible. For example, you can write the question on the paper. Now you can take the photo, ChatGPT free version as a search. You can search it using the photo. That will correctly map to math stack exchange. You have to do it like math stack exchange. That is one of the great resources. Okay. Other than like today we saw one question related to trailer expansion of e power x. No, why shouldn't I ask for 3, or why shouldn't I ask for 97? That is also prime. So this kind of variation is called grouping of variation. Why not 101? Why not 7? I can ask that. No, why not 7? Why not? What about 8? If it is 8, is it going to be reducible? That kind of question. But the real thing, underlying thing, if you start understanding, you can see that this all questions having one thing common. Those kind of comments you can get it from the match tag extension. So when you see my presentation, which is not available in the notes, by the way, but in the presentation, you can see that fun fact. The word I used for younger generation people, but really that's a serious fact. If you start observing this, you can see it is. And the best thing, what I feel nowadays, when you want something like study ring theory, some group theory, go search whatever the best comes. UCLA professors used to write notes. They put it. They don't put it like in the way of books. Some other people, what they do, they take everything. They try to publish a book, but other professors they don't do. 𝐾𝐞𝐚𝐫𝐧𝐿, the best resource, another best resource is Professor 𝐾𝐞𝐚𝐫𝐧𝐿 notes, which is available. Okay, 𝐾𝐞𝐚𝐫𝐧𝐿. Okay, his name is 𝐾𝐞𝐚𝐫𝐧𝐿. All of the ring theory notes are great, and that is really enough to clear exam, interview, and everything. In fact, it is good enough to go second year PhD. I'm sure. One of my professor nowadays, now it is dean, now he is dean, our dean. I worked with him as a TA twice. Both of the time he took all the resources from 𝐾𝐞𝐚𝐫𝐧𝐿 book. Two IIT professor I personally know, those are my seniors. They're also preparing for graduate classes to teach from 𝐾𝐞𝐚𝐫𝐧𝐿 notes. So that's the best thing. Okay, Professor 𝐾𝐞𝐚𝐫𝐧𝐿 notes really enough for theory, practical, everything. If you're able to understand, that's good enough to clear any interview, exam, everything. Okay. For algebra, in general algebra, he has everything. Okay.
Okay, thanks, sir.
Thank you.
Thank you, Dr. Vinod sir, आपको.
Okay, thank you, Dharmendra. So once again, thank you, Jay, for being with us. Okay, let us wind up here. Okay, yeah, once again, thank you, everyone. Bye.
Thank you. Bye.